We are on a collision course with our adjoining enormous system, Andromeda, a collection of a few 100 billion stars. This impact will prompt a mutual descent, dramatically altering both galaxies. Andromeda, crucial in showing that the universe did not revolve around us, has been the focal point of astronomical study for over a century. It was Andromeda that proved the Milky Way was not the only galaxy, revolutionizing our understanding of the universe. While much has been learned from Earth, advancements like the James Webb Space Telescope have provided new, stunning insights about Andromeda that were unforeseen for an entire century. Over 1,000 years ago, the Milky Way was seen as a faint band of light across the night sky due to limited technology that prevented the visualization of individual stars. Different beliefs about the Milky Way placed it at the center of creation. This changed in the early 17th century when Galileo Galilei used his telescope to see that the Milky Way was not just a band of light but a vast collection of stars, planets, and celestial objects. Galileo's work debunked the idea that the Milky Way was the center of the universe, revealing it as a sprawling domain of stars. In 1750, British astronomer Thomas Wright speculated that the Milky Way was a flat layer of stars, including our solar system, a theory limited by the technology of his time. By the early 1900s, significant advancements were made in astronomy. During the 1920s, Edwin Hubble used the 100-inch Hooker telescope at Mount Wilson Observatory to show that distant nebulae, including the Andromeda Galaxy, were separate universes with billions of stars, fundamentally changing our understanding of the universe. The Andromeda Galaxy, also known as M31, has been observed since at least the 10th century when Persian astronomer Abd al-Rahman al-Sufi described it as a small cloud. Al-Sufi's sharp vision allowed him to identify Andromeda without telescopic instruments, an achievement possible because Andromeda is one of the few galaxies visible from Earth's surface without special tools. It wasn't until 1612 that Simon Marius provided a telescopic description, laying the groundwork for future astronomers. In 1764, Charles Messier catalogued Andromeda as M31, advancing its recognition. A major leap in understanding Andromeda occurred in 1864 when British astronomer William Huggins studied its spectrum, finding it distinct from ordinary gaseous nebulae, a critical observation. Andromeda is enormous, with a mass estimated to be between 1 and 2 trillion times that of our Sun, and is believed to be around 10 billion years old, suggesting a complex history of formation through the merging of smaller protogalaxies. Previously, astronomers thought Andromeda was far more massive than the Milky Way, but later research revised these estimates, showing the masses of the two galaxies are much closer than previously thought. Andromeda's physical dimensions are larger than the Milky Way, with a width of around 220,000 light-years compared to the Milky Way's 100,000 to 175,000 light-years, highlighting its immensity. One of Andromeda's fascinating features is its active galactic nucleus, powered by a supermassive black hole with a mass between 110 and 230 million times that of our Sun. Observations using advanced telescopes like the Hubble Space Telescope reveal 2 points of focus in the Andromeda Galaxy, with the brighter one slightly off the true galactic center, indicating intense gravitational interactions and the presence of the supermassive black hole. Andromeda also has an abundance of globular clusters, estimated at around 460, each containing hundreds of thousands to millions of stars. This abundance demonstrates Andromeda's history of galactic cannibalism, where smaller galaxies were absorbed into Andromeda, adding to its stellar population and diversity. Recent observations suggest that Andromeda may transition from a typical spiral galaxy to a ring galaxy, a relatively rare type characterized by circular, ring-like structures of bright young stars. Ring galaxies can form through galactic collisions or when a smaller galaxy passes through the center of a larger one, making them unique among galactic structures. The impending collision between the Milky Way and the Andromeda Galaxy is a cosmic event predicted to begin around 4 billion years from now and will unfold over the following 2 billion years. This grand encounter will culminate in the formation of a new supergalaxy, which has been informally nicknamed Milkomeda by astronomers and enthusiasts. The merging process will be characterized by significant gravitational interactions and tidal forces, dramatically affecting both galaxies. As the Milky Way and Andromeda approach each other, their immense gravitational forces will start to distort each other's shapes. This gravitational exchange will pull stars, gas, and dust from each galaxy, creating elongated tidal tails and triggering a series of complex gravitational interactions. The overlap and merging of the two galaxies will not be a smooth process. Rather, it will be marked by chaotic and dynamic changes as their structures are gradually torn apart and reformed. Transformed, one of the most emotional results of this crash will be the development of new star groups. As the universes blend, the gas mists within them will impact and compress, prompting explosions of star development. These heavenly nurseries will be regions where extraordinary gravitational forces compress the gas to the point of breakdown, forming new stars. These newly formed stars will often be grouped into clusters, enhancing the new supergalaxy with new stellar populations. Simultaneously, the gravitational chaos will cause changes in the orbits of existing stars that were already in stable circles around the center of the Milky Way or Andromeda. These stars will be tossed into new, more elliptical paths or possibly flung out of the merging system altogether. Some stars might find themselves ejected into intergalactic space, becoming rogue stars, no longer bound to any galaxy. This rearrangement of stellar material will add to the development of new cosmic structures and may result in a complex web of star streams and clusters that blend the remnants of the two galaxies. In addition to forming new stars and clusters, the merging process will also create massive, complex structures within the new galaxy. The gas, dust, and stellar debris from both galaxies will mix and settle into new configurations, forming vast regions of star formation, twisting arms, and potentially new cosmic features that are a hybrid of both the Milky Way's and Andromeda's original structures. These structures will evolve over time, influenced by the new dynamics of the merged galaxy. The supermassive black holes at the centers of the Milky Way and Andromeda will also play a significant role in the merger. As the galaxies coalesce, their central black holes will eventually merge, creating a single, even larger supermassive black hole at the center of the new galaxy, Mila. This merged black hole will be a powerful source of energy and will have a profound effect on the surrounding stellar environment, contributing to the galaxy's dynamic and evolving structure. Ultimately, the merger between the Milky Way and Andromeda will result in a completely transformed cosmic landscape. The new supergalaxy, Mila, will be a giant entity made up of the combined material from both precursor galaxies. It will feature a rich tapestry of new star clusters, altered stellar orbits, and restructured galactic features. This process of cosmic evolution, driven by collision and merger, will shape the future of the local group of galaxies and provide a fascinating glimpse into the long-term dynamics of galactic interactions. The merger will bring significant changes to our night sky and the environment on Earth, potentially affecting habitats, biodiversity, and climate. However, this process will occur long after humanity is gone, as our sun will expand into a red giant and render our solar system uninhabitable in about 5 billion years. The merger of Andromeda and the Milky Way raises questions about the fate of our solar system and the formation of new galactic structures. The cosmic interactions may shape a new cosmic environment, possibly with habitable zones for potential life forms, though vastly different from what we know today. The Mila galaxy will be a testament to the dynamic and ever-changing nature of the universe. The collision between the Milky Way and Andromeda, predicted to happen in about 4 billion years, will be an event of cosmic proportions. It marks the culmination of a gravitational dance that began billions of years ago when these two giant galaxies first started their inevitable approach towards each other in the vast expanse of space. As the merger progresses, one of the key phenomena astronomers anticipate is the transformation of the two galaxies' spiral structures. Currently, the Milky Way and Andromeda are spiral galaxies characterized by their prominent arms extending outward from a central bulge. These spirals are defined by the rotation of stars and gas around a central core, creating distinctive patterns observable from Earth. However, as the galaxies move ever closer, gravitational interactions will intertwine, and these spiral structures will undergo significant changes. The mutual gravitational attraction between the Milky Way and Andromeda will distort their shapes, pulling and stretching their spiral arms into elongated tidal features. These tidal streams will be made up of stars, gas, and dust that have been pulled away from their original galactic disks, creating a turbulent yet beautiful cosmic scene. Hypnotizing show across the infinite scene, the crash will likewise trigger extraordinary eruptions of star development inside the newly forming superworld. The connection of gas mists from both galaxies will pack and heat up, prompting the development of massive, iridescent star bunches. These clusters will become the nurseries for young stars, whose vibrant radiation will illuminate the surrounding astronomical dust and gas, bringing forth new heavenly populations. The merging process will not only affect the presence of the galaxies but also their inner dynamics. The gravitational interactions among stars and gas clouds will cause a reshuffling of their orbits and speeds. Some stars will be flung into more unpredictable orbits, while others may be ejected entirely from the merging system, becoming free-floating rogue stars in the intergalactic void. Meanwhile, the very large black holes at the centers of the Milky Way and Andromeda will play a crucial role in shaping the fate of the merged universe. These behemoths, each millions of times more massive than our Sun, will eventually spiral toward one another, influenced by gravitational waves emitted as they orbit closer and closer. The final stages of the black hole merger will be cataclysmic, releasing vast amounts of energy into space as gravitational waves and radiation. This merger event will create a single, even more massive supermassive black hole at the core of the newly formed galaxy, surrounded by a swirling accretion disk of gas and dust. The presence of such a powerful central engine will have significant implications for the evolution of the superworld. It will regulate the formation of stars and influence the dynamics of gas and dust within the galactic core, potentially triggering quasar-like phenomena as material falls into the black hole and emits intense radiation across the electromagnetic spectrum. On a larger scale, the merger of the Milky Way and Andromeda will contribute to the ongoing growth of cosmic structure in the universe. Galaxy mergers and interactions are key processes in the hierarchical growth model of galaxies, where smaller structures combine to form larger and more complex systems over cosmic time. Studying galactic collisions like the one between the Milky Way and Andromeda provides astronomers with insights into the mechanisms driving galaxy growth and evolution. By observing how stars, gas, and black holes interact during such events, scientists can test theoretical models of galaxy mergers and refine our understanding of the physical processes at play. The merger will also have implications for the distribution of dark matter within the newly formed supergalaxy. Dark matter, an invisible and elusive form of matter that makes up a significant portion of the universe's mass, plays a crucial role in shaping the structure of galaxies and their gravitational interactions. During the merger, the gravitational forces exerted by the dark matter halos surrounding the Milky Way and Andromeda will interact and merge, influencing the overall distribution of dark matter in the new galaxy. Observing the effects of dark matter during and after the merger will provide valuable clues about its nature and properties, helping astronomers unravel one of the biggest mysteries of modern cosmology. The merger between the Milky Way and Andromeda will also provide a unique opportunity to study the formation of galaxy clusters and superclusters. These vast cosmic structures, composed of multiple galaxies bound together by gravity, are the largest known structures in the universe and offer insights into the large-scale distribution of matter and the formation of cosmic web-like structures. As the Milky Way and Andromeda merge, they will bring their respective satellite galaxies into play. These smaller galaxies orbiting around their larger companions will be gravitationally drawn into the merger process, either merging with the new supergalaxy or being torn apart and absorbed into its extended halo of stars and gas. The fate of these satellite galaxies will depend on their orbits and velocities relative to the merging Milky Way-Andromeda system. Some may survive the merger relatively intact, becoming dwarf galaxies within the new supergalaxy, while others may be disrupted and ultimately absorbed into the larger structure. The merger between the Milky Way and Andromeda will also have implications for the cosmic environment surrounding our solar system. While the crash itself will not pose a direct threat to Earth, the gravitational disturbances and influx of cosmic rays from the merging galaxies could have subtle effects on our planet's climate and cosmic ray exposure over long time scales. Additionally, the formation of the new supergalaxy, Andromeda, will create a fundamentally different night sky for any future inhabitants of the Milky Way. The merger will rearrange the positions and distributions of stars, star clusters, and nebulae, potentially creating new constellations and celestial landmarks that will shape the cultural and navigational aspects of any civilization that arises in the distant future. In conclusion, the collision and merger between the Milky Way and Andromeda represent a cosmic spectacle on an unimaginable scale. It is a process that will transform both galaxies, creating a new supergalaxy that blends the material and characteristics of its progenitors into a unified cosmic entity. From the reshaping of spiral arms and the birth of new star clusters to the coalescence of supermassive black holes and the redistribution of dark matter, every aspect of the merger will leave an indelible mark on the future evolution of the local group of galaxies. Studying this event provides astronomers with a rare opportunity to witness the transformative power of gravitational interactions in shaping the universe we inhabit. It is a reminder of the dynamic and ever-changing nature of cosmic evolution, where galaxies collide, merge, and ultimately lead to new structures and phenomena that continue to inspire wonder and curiosity in the exploration of the universe.